given this year. He's on sabbatical, he's on a break, so he's traveling a lot. And so that's one reason why he came here. The schools he's been to: Columbia, Harvard, Dartmouth, Boston University, MIT, bunch of pretentious schools. And then there's UNH right now next to him. So I'm very happy about this catch. He's a really awesome guy. Looking forward to it. Please come if you're interested. Okay. Now back to our regularly scheduled program. The last class on Thursday, we introduced the concept of enthalpy. This idea of being able to measure the heat content of our substance and subtract out all the PV part of the energy. And we did that by making the pressure constant, basically opening the top of our flask, allowing the system to equilibrate the atmosphere. That allows us to ultimately equilibrate the PV work. We don't really worry about PV because the pressure is constant. And we saw that by looking at condensed materials, where if we do some change of our condensed material, base of liquid, we do a chemical reaction to it to change its constitution. They were converting water to hydrogen peroxide or vice versa. The density doesn't really change that much. The material doesn't change that much in terms of its physical compactness. Densities or changes are small in liquids. And so that, therefore, the PV part of the energy is very small. So we can neglect it, and we're left ultimately at constant pressure with just the heat content of the material. So what I want to do today is, that's a very, very abstract and general way to think about enthalpy. So changes in enthalpy are changes in heat content, internal heat content of the material. I want to make this more chemical today. There's two things that we need to answer. First, what the hell is the heat content of a material? What does that really mean? We'll look at that today. And two, how do we measure it, right? And what do we measure relative to? Once again, the change in the enthalpy is a change in the heat content. It's all about relative changes. And so if we want to measure enthalpies in like an absolute sense, we want to measure exothermicity, endothermicity, whatever, stability, we need to have some reference to compare it to. We need a reference energy so we can calculate everything as differences to that reference. No absolute. We got to set like the 0 point. What is zero enthalpy? What's that defined as? So we'll answer that question today. To kind of give us what we call the chemical energy scheme. What do we define energy relative to for chemistry? And that'll get us a really, really good place together, right? We'll understand enthalpy. And then what we'll do kind of next class is to connect it to entropy. Now we have enthalpy and entropy, and you guys know when you combine entropy and enthalpy, you get Gibbs free energy, H minus Ts. So we're very close to getting Gibbs, and Gibbs is going to be kind of our tool that we'll use going forward to measure anything energetic, any sort of energetic process in chemistry. It's kind of a nice, complete tool for us, but we got a bit of a ways to go. So let's think about the chemical definition of enthalpy. Right. So I want to think about it in terms of, let's just do it in terms of pure substances, right? So we're just going to pick a molecule and then like have a liquid. Okay, let's just pick an example molecule. Let's take an example. Does anyone have a favorite molecule that they'd like to use as an example? So, what do you got? Your benzene? What do you got?
THC.
I can't draw that. I'm gonna go with benzene because that's easy to draw. So let's take benzene for an example. That's not benzene. Okay, and let's have a mixture of a container of benzene at some concentration, or some concentration, some condition. So we could set it to, let's say, 300 Kelvin. Just like before, we go set a constant pressure. Pressure is 1 bar. What's the enthalpy of this? What's the heat content of this material? So And let's just say, oh, sorry, let me add one more. What is the enthalpy of this material? How do we even calculate? What do we need to, I mean, what does it even mean? Well, let's think a little bit about how, right? Remember that energy in a gas or a liquid is expressed through motions, different types of motions that the material can exhibit microscopically. Right? We thought about, I remember in problem set 1, you had that box that you cut in half and you calculate the entropy change. You let the box, the molecules distribute from the left to the right. Right? And there, the motions are basically exchanges of the atoms across the left and right boxes. We've introduced some motion to the system that changes the entropy, because now you can either have left molecules or right molecules, and that introduces some combinatorics and some permutations, which increases the entropy of the system. But so we know that we can understand then that the energy has something to do with the available motions. What are the available motions, and what's the heat content of benzene? So let's kind of break it down a little bit. What kind of things is benzene doing? Well, first of all, we have a liquid. We assume a liquid. Right? We have benzene molecules that are all kind of crunched together in this liquid. They're moving around, right? So they have some flow and some motion. We have some like diffusion, flow, random XYZ motion. You can imagine if I have a bunch of benzenes, I'm just going to draw benzenes as little circles. They're little benzenes in a liquid, and I have one in the center that I'm looking at, right? And this can bounce back and forth. Right, and it has some motion, right? There's some translational motion. And so some of the energy is required, some of the energy is used up for this translation. You can even calculate how much energy it is. Benzenes have other options. And any molecule has this. What are some other things that it can do? Well, again, we talked about this when we talked about our boxes for the first time. We talked about the PV work where everything's pressing against the boxes, but there's also these other motions that are in the heat, which is like the rotation of the system. So benzene can rotate. So I can have my little benzene, a little benzene molecule embedded in a solvent of benzenes. I got a bunch of benzenes around it. I've got some distances. And that single benzene can rotate like so. Rotational motion. Just as a note, this is what I study. This is literally what my PhD is in rotational motion of molecules. I study rotations. Lots of interesting things you can learn about molecules from studying their rotations. It's not on the test, by the way. Perhaps what is more relevant to molecules, especially polyatomic molecules at 300 Kelvin, is that they vibrate as well, having these internal motions. The molecules can also vibrate. And I'll try to show you an example of that. In fact, while I write this, I'm going to boot something up for you. And in fact, for benzene, so for N atoms, a 3N minus 6, sorry. Okay. For N atoms, a 3D molecule, the molecule that is in a line, has 3N minus 6 vibrations. We'll learn that next semester. Okay, so there's a bunch of different ways that benzene can wag itself and shake itself off. Right, there are 12 atoms in benzene. So there are how many modes? There's 3 times 12, 36. 12, 24, 36 minus 6. There's 32 different vibrations that benzene has. And maybe one of them is where these hydrogens stretch like this. The hydrogens on the side stretch. And the ones on the edges, the top and the bottom come inside. Like you have this like stretching motion like this. And there's, how many did I say? 36 minus 6. So there's 36 minus, yeah, 29 numbers. Okay, and there's a couple of other types of motions, but at 300 Kelvin, we don't really worry about that. The electrons themselves in the benzene will get excited. That's what we call electronic motion. That doesn't really happen at 300 Kelvin. So by and large, the 3 motions that a molecule does in a liquid at 300 Kelvin is a mix of diffusion, moving through the material, rotate, and they can vibrate. And so if we have just a molecule by itself, then the total energy of that molecule, write this on the left, the enthalpy of that molecule is equal to the translational kinetic energy of the molecule. So if it's moving around, plus the vibrational energy, what kind of vibration it has, plus the rotational energy. Okay, well, if the molecule is at 0 Kelvin, has no energy, then you would say the enthalpy is 0. Right? So because it doesn't have any energy, if we strip out all the energy, then H is 0 for this system. Right? Because it doesn't have any energy that molecule isn't expressing the energy in any way because it has none. Right? But here's the crux of the problem, right? I just defined and said that the energy of benzene, the enthalpy of benzene is 0 at 0 Kelvin. I mean, there's nothing wrong with that statement, but there's a problem. What if I picked another molecule that was C6H6? Different system. I don't know how you would draw that, but something that wasn't benzene, something else that had 6 carbon atoms and 6 hydrogens arranged differently. And we took that to 0 Kelvin, we would also say that the enthalpy is 0. But those 2 molecules are different. They can't be at the same energy. They're different structures. They have different stabilities by definition. Only things that have same energies are same molecules. So I can't really define this to be H equals 0 because every molecule at 0 Kelvin has 0 in its definition. So this doesn't work for us. This is a problem because it isn't unique. Right? It's 0 for all molecules at 0 Kelvin. Right? So that's a terrible way to define the energy, the enthalpy, right? The heat content, because everything is shared at 0. So there's no way to compare anything. I imagine you have 2 molecules, you want to know which one's more stable than the other. Well, you put them both at 0 Kelvin, they're exact same energy. But that can't be the case. They have to be at different energies because they're different molecules. There's some other internal energy difference that we're not accounting for in this difference. Right, so we have to rethink things a little. Right, we need to have some sort of scale. We need to set enthalpy to be 0 in such a way that allows us to differentiate between different molecules at 0 Kelvin. Right, the reason why I choose to do things at 0 Kelvin is we'll see 0 Kelvin is not a physical number. You can't reach absolute 0. I've been proving that to you up in the world. So 0 Kelvin is just like an abstraction in our idea. The idea is that we're taking a molecule and putting it in a vacuum and freezing it out, and we have no heat at all. Okay, you can imagine that being the case. That's reasonable to do. You can't maybe physically do it experimentally, but you could certainly construct this in your mind or on a computer. Think about what the energy of a molecule is without any heat. Just the intrinsic internal energy of a molecule. Strength of all of its bonds, its vibrations. So this doesn't work. So we need to have something that gives us unique solutions, unique energies, relative enthalpies that are all referenced to some absolute scale that allows me to distinguish between benzene and something else that looks like benzene. And so what we should do instead is think of chemistry as like Legos. And what we should do is think about set the energies of the fundamental building blocks of all molecules to be zero, and then everything is relative to them. So imagine that you're building a Lego set, you're building a molecular Lego set, and you want to calculate the energy, the net energy of some construction you make. And what the assumption that we're going to make is we're going to assume that each little 2x2 piece that you use to build your molecule, or some primitive of your Legos, apply zero energy. Therefore, when you have this net construction of all these atoms, there are, because of the way that you've constructed the building or whatever you're building your Lego set with the target of your Lego construction, whatever you're building, each little primitive element, each little piece contributes no energy to the system, but what you now measure is the net energy of the construction itself. Right? Your building that you've built or your molecule that you've built now has some strain energy, right? Because you've got things hanging, you got gravity affecting. Right? Gravity doesn't affect one piece, but when you stack them up 6 feet high in a really, like a tower of cards, you have strain energy, right? The system is now supporting itself against the force of gravity. And so therefore there has to be some potential energy in the construction itself that's resisting the force of it falling apart. So you've taken some system that you started from these little elements that have zero energy themselves, and your net product, your net construction now has non-zero energy, and all of that energy that is now created in some sense is relative to when all the pieces are separate. So what you've measured, that change in enthalpy from the enthalpy of all the pieces having zero energy to your building having some energy, that energy change is just the energy constructed from the construction itself, right? The strain forces and the gravitational strain and the effects of gravity and weight affecting your build. All right, so what we're going to do is define a set of primitives, chemical primitives, that we can construct any molecule from that have their enthalpy to be zero by definition. So any enthalpy change that we measure after we construct has to have come from the construction itself. Right? So what we're going to do, we have to think logically about what choices do we want to make. We can make any choice we want. We can set hydrogen atoms to be zero energy. But that doesn't really make a lot of sense chemically. We should choose molecules that are so stable and so ubiquitous as our primitives, or atoms that are so ubiquitous that in some sense there isn't an arrangement of them that is more stable. Right? In some sense, like if you think about oxygen, we want to think about the energy of things constructed from oxygen. We should choose as the thing that has oxygen in it that we use as our primitive, H0, to the form of oxygen that is most stable at typical conditions. What do we most commonly find oxygen in? So our criteria are stable and ubiquitous at standard conditions. What do I mean by that? So if the example is if we define standard conditions, the 298.15 Kelvin, right, room temperature, and a pressure of 1 bar. And let me ask you this one, what is the most common form of oxygen atoms found at these conditions? That's a question for you guys, right? So if I want to define a primitive that defines stable oxygen to a typical chemist at 1 bar and 298.15 Kelvin, what kind of form is that oxygen in?
O2.
Gas.
O2 gas, right? Because think about it. What we breathe in is O2 gas, right? That's the most stable thing. We don't have oxygen atoms. Oxygen atoms are not stable at room temperature, right? You have to crack oxygen, O2, in order to make oxygen atoms too. Right? So at standard conditions, oxygen is only O2. So that's the definition, right? Of that we could say now that we can do is set the enthalpy of oxygen gas to be 0 kilojoules per mole. Right? And that means then if we could look at, then for example, right, if we then consider the cracking of O2, right, we now have an enthalpy change, right? This reaction now is endothermic or exothermic because we've taken a system that has 0 energy by definition, 0 enthalpy, and we've broken it apart, right? We have to break that bond. So the enthalpy of O obviously is going to be positive, right? Because we have to put energy in to break the bond. Right? So the enthalpy of this reaction, we could say delta H, whatever it may be, is greater than 0 by definition. It's endothermic. Right? Because we have to put in energy into O2 to crack it. Right? In fact, I learned this the hard way in my postdoc that this doesn't happen with heat really until you hit about 2000 Kelvin. Oxygen spontaneously falls apart around 2000 Kelvin. It cracks in certain environments. So you have to put energy. You have to heat it up. Okay, and so we can just go down the list of all the atoms and say what's the most common form of these elements. So let's just go ahead and pull up a periodic table. In fact, I'm just going to copy it over. And we'll look at this a little more carefully, but right, so we can just kind of go through this list and say, what are the most common arrangements or the common setup for each of these atoms that we expect at standard conditions? Right, so let's just take it step by step. What do we expect H to be in at temperature and room pressure? The H atoms?
Gas.
Gas of what?
H2.
H2. Right, so the standard condition for hydrogen is H2.
So it doesn't necessarily have to be like, would we find it? It's just if you had it as standard.
Right. What's the most stable form of it?
Okay.
Yeah. So the definition. This is a international standard for enthalpy. It's the IUPAC standard, which is to say each atom is constructed. We define the energy scale to be constructed from assuming that each atom comes from the most stable form of its type at standard conditions, which is 1 bar room temperature, right? STP. So H2, right? And of course, helium is by itself, right? So the standard form of helium is helium in gas. Carbon is very interesting. How would we define carbon? Tricky one, isn't it?
Graphite.
Ah, great, graphite. Right, graphite, because it turns out that diamond, you could potentially use diamond. There's no reason not to, but again, diamond only forms at high pressure. Graphite is much more common at 1 bar. In order to create graphite, all you need to do is just burn off, take a hydrocarbon and make it into tar. That's basically what graphite is, but you just burn all the hydrogens off of it, you just have carbon. In order to make diamond, for instance, you would need to take all the atoms and compress them at very high pressures to form diamond. Diamond's in some sense a higher energy structure, even though it's quite stable. But it requires you to put heat and PV work in to convert it. So carbon, you just take the natural choice, which is a solid form of carbon, which is graphite, the stuff in your pencil. Right, and I could just go down this list, right? N2 for nitrogen, ox gas. O2 for nitrogen or oxygen, right? F2 for fluorine, and so on and so forth. Right, so you get the idea. Okay, eventually you get to atoms where they generally are stable at their typical form. Like titanium, we typically just take solid titanium neutral. So this one would be titanium neutral solid. Interestingly, like there's some strange ones though. For instance, sulfur. Sulfur is the octamer of sulfur in a solid form. And since there's lots of different choices, and these are all just come from empirical measurement. They're just the things that chemists typically find these atoms in that are stable and they're plentiful at room temperature and room pressure. All right, so these are some examples. So every atom is assigned a primitive where H is equal to 0, such as these. Okay, so everything can be measured now relative to these. All right, let me show you an example of where this comes up. So you may wonder where these are tabulated, for instance. I'm going to show you a website today, and I'll post these online. They'll be useful for the homework later on. There's 2 different websites I'm going to show you. This one is actually from my old postdoc position, Argonne, Chicago. This is the Department of Energy site. At the thermochemical tables. This is run by the guy who was my neighbor in my office. And this is the global home of standard enthalpies for molecules. These are the most accurate ones in the world, and they're constantly updated. And so let me just show you an example, right? We could just kind of go through the list. And here you can see as I go, the first set of lists of molecules on this list are all the primitives. H2, He, boron, crystalline liquid, graphite, nitrogen, oxygen, fluorine, neon, silicon crystalline, sulfur crystalline, Cl2. Notice how all the enthalpies are 0. They're exactly defined. So all of these are just the common, and again, this is not a complete set of enthalpies, but most of the common ones we use in chemistry, they're all set to 0. Okay. So any enthalpy that we use to define a molecule's enthalpy is all defined relative to these numbers. So let me show you an example of that. Right, so let's go back and do an example. This is an example that I looked at a couple lectures ago. Right, and I want to calculate delta H for this. Okay, so how do we do that? Right, well, remember the enthalpy is what we call a state function. It doesn't really depend on anything in the middle. It just depends on the endpoint in the beginning. So the change in enthalpy is going to be equal to the enthalpy of the products minus the enthalpy of the reactants. And so our products, we get 2 moles hydrogen, 3 moles of gas on the other side. So in order to keep all our moles balanced, we need to apply the stoichiometric ratios here. So we're going to have 2 times the enthalpy of H2O. That's our product. And then we're going to sum over the reactants. That's 2 times the enthalpy for H2 plus 1 times the enthalpy for O2. Now, you guys probably remember doing this in Gen Chem a million times. Same as that process, right? But this is a really easy calculation to do, right? Because H2 and O2 are standard conditions, standard materials. These are by definition 0. Right? So these are by definition 0 because these are our primitives. So that means that the enthalpy change of this is just the enthalpy of water. Right. So in order to calculate this energy, we need to know the enthalpy of water. You see the problem now is that we've kind of done a circular motion, right? Right. So we have to figure out some other way to calculate this. I haven't really helped myself. Now, how would I do that? Well, in experiment, it's very easy for me to do this. Experimentally, all I have to do is put my system at constant pressure and take 2 moles of H2 and 1 mole of O2 and measure how much heat change my system has, right? Measure the temperature change of the system, right, at constant pressure. So we'll leave it, we'll have the temperature vary. We'll just leave the pressure constant, that gives us enthalpy. And we'll see if the temperature goes up or goes down. If it goes up, then it's endothermic and H2O is positive. If it goes down, meaning the system releases heat, then we know the enthalpy is negative. Right? So all we have to do is go measure the heat change, go measure delta T in a constant temperature reactor. Right? You can go do that and you get a number. Or we can go look it up. Right? Someone's done this experiment before. Or if we're lucky, it's already tabulated. We can go look it up. So let's go look it up. So I'll go here and I'll type in H2O. And you can see there's lots of different choices for H2O, but they're all in different states. Right? We have liquid, gas. I don't know what compress is. This is para and ortho are different magnetic states of water. Water has 2 magnetic states called para and ortho. They have different energies. Put water in a magnetic field, for instance. You see that, but we want the liquid form, right? And we see that at delta at 298.15 that the enthalpy is this minus 285.8. So we saw that the enthalpy of H2O at 298 Kelvin, what did I say it was? 290 something? 285.8 minus 285. It's 285.8 kilojoules per mole. Right? And so the total enthalpy change of this reaction is 2 times that. I'll just round it to 286. I'm too lazy to do that math in my head. minus 572 kilojoules. Right, so we would expect that when we do this reaction, we mix 2 moles of H2 and 1 mole of O2 to get them to make water. We should expect a heat release of 570 kilojoules per mole. Okay, so this reaction is exothermic. Now you may think, we have to think about this a little bit, right? What this is saying is that when we have a container containing 2 moles of H2 and 1 mole of O2, it has some heat content and some energy. And when they react to form 2 moles of liquid water, suddenly there is much less energy in the system. It's released 500 kilojoules of mole of energy. Right? And as I talked to you guys last time, that's a combustion relevant amount of energy. That's about as much energy as a mole of octane releases when you combust it. It's a lot of energy. Right? And so you would think that logically, what does that mean? It means in some sense that H2O, right? This is what and we're gonna have to. I'm gonna have to try to beat this bad habit. Maybe it's not a bad habit. But that would think, okay, well, if this is the heat content here, and this is the heat content here, and it's 500 some kilojoules per mole less, then water is more stable than O2 and H2. It has less energy. When we've talked about in this class over and over again, that chemistry likes to be lazy. It likes to be as low as energy as possible. Stability means low energy. Right? So we've lowered the energy by 500 kilojoules per mole. We can say, oh, that must mean it's stable. Right? H2O is stable compared to O2 and H2. But you have to be very careful with that statement. Because stability means something about kinetics. Stability means something about how long something lasts. Right? And let me tell you this, if you take O2 and H2 at room temperature, you mix them together in one bar, you put them in a tank, and you let that tank sit there for 50 years. You don't touch it, just leave it sit there. You come back and you measure the water content, and there's no water in there. But we just said that this system loses energy and releases heat readily. Very, very exothermic. But I just claimed that when you mix those two gases together, they never react. So that's a measure of stability. What this is saying is that even though this is thermodynamically exothermic, you're losing energy, releasing energy as you go from left to right. It's not to imply that water is more or less stable than the original gases. The stability has to do with how, when you have these two together, how long do they stay together in this arrangement? But I just claimed that basically at 300 Kelvin, this reaction never goes. It doesn't happen. And so stability is something about kinetics and about time as well. So we're going to have to distinguish in some sense between energy differences and fast kinetics. Something that's unstable is something that it's exothermic, releases energy, but also does it very quickly. Basically, the moment, if these were unstable, the moment you bring them together, they would react violently, and you'd form water. Of course, if that were the case, we wouldn't exist here. We would just be in a giant, our atmosphere wouldn't exist anymore. Because if H2 and O2 combined spontaneously and release 600 kilojoules per mole, we would flame out the entire atmosphere, burn it all up instantaneously. Okay, so that's stability. Stability is about temporal stability. It's about when two molecules come together, do they react? And what we'll learn is that even though two molecules can react and form something much more stable than them, it still takes a lot of energy to break these bonds. You still have to break this oxygen bond and these hydrogen bonds and get the atoms to move together. That takes a lot of energy. So stability also has to do with an intermediate step. There's some rearrangement of these atoms that have to be facilitated to get to this endpoint. And that rearrangement, as it turns out, takes a lot of energy. So what you have to do is the energy, in order for this to happen, the energy has to go way up before it goes way down. And so that additional energy barrier, which is the barrier of breaking the O2 bond and the H2 bond, is what keeps these stable. Try to distinguish between stability and energy differences, all right? And I'll try to make those, it's a very subtle point, and it's one that I'll continue to make as we go through this semester. Now, in fact, though, this is not a particularly useful way to measure the enthalpy of H2O by using this reaction. In fact, there's a really great paper by the author of ATCT that talks about this, that doing this reaction is not very easy. It's very hard to control experimentally. But here's the thing, if we can, in some sense, imagine that we can, from some primitives, these primitives, we can make some other molecule that then decomposes or reacts with something else, form water. And imagine we make a loop instead. So what about this, right? Imagine that we want to know delta H for this general reaction. A plus B goes to C, right? Where the enthalpy of A is equal to the enthalpy of B, which is 0. Okay, so they're primitive. Right, but imagine that doing AB going to C is not very practical. Very hard to control. And in fact, H2 plus O2 is extremely hard to control. We'll return to that reaction later on in the class. But what can I do instead? Well, what if I do this instead? Where I took A and I made A prime. I made some new molecule, right? And I can measure delta H very easily this way. Okay? Easy to measure. Right? For instance, maybe I can use spectroscopy. And then I take B and I make B prime. And this conversion is also really easy. And then what I do is I take B prime and A prime to form some intermediate molecule D. And this is easy. And then D just naturally composes into C. Right? What's the net reaction? Right?
A plus B. goes
Well,
to C.
like, don't ruin it for all of us. Give me a second.
Sorry.
All right, that's okay. It wasn't a question to you guys. I'm asking rhetorically. I'm sorry. Let's just work the math out. Okay. So delta H here is going to be the enthalpy of A minus the enthalpy of A. We'll call this A. B is going to be HB minus HB. The enthalpy of this reaction, which we'll call BA, is the enthalpy of D minus the sums of enthalpies of HA plus HB. And then finally, we'll do HC here. We'll call it HC because that's easier. This is HD minus HC. Sorry, I have that the wrong way. Products minus reactants. HC minus HD. All right, what's the total enthalpy? Well, total enthalpy change is just the sum of all three. Right. And let's just do the algebra. Right. So the HAs cancel out. Oh wait, no, sorry. Oh, sorry, I forgot the primes here. Sorry. There we go. Great. So the HA primes cancel out. The HB primes cancel out. The HD prime cancel out, and we're just left with HC minus the sum of HA plus HB. which is the original reaction I wanted. What did I call that? Just whatever that, which is the target reaction. Right. So what I can do is I can basically make loops, right? If I can measure some intermediates and then measure those intermediates decomposing to the final product, right? I could just add steps in the middle, then I can still get to the right answer, right? By decomposing my hard to measure reaction into a series of easy to measure reactions. Right, there's a term for this. This is what's called, I don't know if your Gen Chem professor ever called it this. This is called Hess's law, which says that the total enthalpy is just the sum of all the steps. The total energy for any process is the sum of all the intermediate steps. Right, so let me show you how this works in practice. And this is why I like ATCT so well. This is a really cool website. It shows you how he calculates these numbers. So there's two different ways, in some sense, traditionally to calculate enthalpy. So let me show you those. So before I do this, let's do the simpler one. This is another website I'll have you guys use on the homework, this web book. And let's go to the water. Right, we're interested in the formation, the enthalpy of water, right? That was ultimately our the thing we were interested about was how do we measure the enthalpy of water? And I can click it here. And you can see that I get a nice value here, 285.83. It comes from some paper. We can click that paper to see what kind of method it is. It's just it's been collated from some other measurement. All right, so someone measured this somewhere and CodeData measures it and reports it. Okay, so that's not very helpful, right? It doesn't really tell us anything about how that number was measured. It turns out that typically what happens is people have studied these things so many times, they take an average. They have a couple different answers, and then you take an average, and then CodeData decides that's a reasonable average of the data, and we'll report that as the reference. But that doesn't really give you any chemical insight about how this number was determined, right? That's the problem why I don't really like this approach and why ATCT is so cool. The way ATCT does this is it looks at takes water and says, let's look at the entire database of every thermodynamics or thermochemistry measurement people have done to measure the enthalpy of some reaction, heat of reaction, and isolate all the ones that contain water in it, right? And by using Hess's law, you can say, well, if I have all these different random reactions, if I add them together in a certain way, I should be able to cancel everything out and just left with water. And so that's how he does it. So he just takes this giant network of reactions that all connect water to a bunch of different intermediates and looks at the enthalpy for those reactions that are measured and statistically pulls out the enthalpy of formation that would be consistent with waters. Because they all have to agree, they all have to share the same enthalpy for water. And so if you have all these different reactions that can contain water, there must be some average value of the water enthalpy that satisfies all of those enthalpy calculations. And he tabulates them. So if I click it for liquid water, somewhere. Yeah. So here we go. So he has here a table, different weights that he determines statistically about how he determines how to pull what enthalpy data, what reaction data to pull out to weight to measure through Hess's law the enthalpy of water. Right, so there's the first example. So the biggest example is the water cracking reaction we just looked at. So for water, most of it comes from measurements from back in 1930 of this exact reaction. Right? And they measured the reaction enthalpy minus 285.8. Right, but then he also looks at what's called I forget what this is called. Well, this is just combustion. Right, here's the combustion of methane. That's another thing that people have measured very accurately for a very long time. First, that makes 2 moles of water. Right, and that generates this much energy. We know a fraction of that energy is the 2 mole of water here. And so you've got like an unsolved variable. You've got x here, you got 2x here. And you sum all these up and they're equal to this. So you have this system of equations. Right? We have x minus 0. This is x minus 0, 0 is equal to this. This is 2x plus this is equal to this, and so on and so forth, right? Hydrogen plus graphite to make this is CH activation of carbon. Here's water cracking and the gases. This is the ionization of OH radical. Here's the breaking of OH and H from H2O. Right? You kind of some set of fairly exotic reactions as we go down. Some of these are pretty weird. But you can see that water is included in all of them. And these are all reaction enthalpies that are measured, right? He's not measuring individual contributions, just saying that, hey, I've got all of these enthalpies of reactions that are all statistically or algebraically connected to some number of waters. 2 waters on the left-hand side here, 1 water here, and so on. And he goes in and says, okay, well, whatever the water may be, enthalpy may be, it must optimize all these numbers, right? They all must be consistent with these. And then you also have to then do it for CO2 and H2 and CH4, right? You've got a bunch of other things you have to solve. So you have this big, long network of basically algebraic equations, just doing thousands of enthalpy calculations, differences of products and reactants, and solving for the unknowns, right? The enthalpies of each of the materials.
Please tell me a computer does that.
Oh, yes, of course.
Yeah,
of course.
Praying.
This is all done computationally.
Well, because
Yes.
when you keep saying he, I'm like, oh, this is one.
All right, so they introduced,
Yeah.
so Bronco,
I'm just hoping that he wasn't sitting there slaving away on a whiteboard.
no, well, actually, yeah, maybe he was. Bronco is an Excel god, and he does most of his work in Excel. He has like 50 megabyte Excel spreadsheet. Just crazy. He's got this calculator, he sends them to me. If you need a molecule, you want to know the enthalpy of it at any temperature. We'll talk about this next class. The enthalpy depends on the temperature. And he has these calculators that he gives you for a molecule. You type in the energy, and he calculates the exact enthalpy for the molecule at any temperature you want. Very, very precise. What he does, the thing that he spent the most time doing is not the algorithm. That's all the computer. It's picking what are good measurements to use in the data. It's the data set that's the hard part. And so every time he updates it, it's not that he's improving the routine, it's that he's adding new papers and removing bad ones.
So he's just looking for like reliable papers and
Right.
last people
And
who
of
have
course, things get better every year too, right? We make
Yeah.
things more accurate.
apparently not for the 1930s ones.
Well, so again, this is these reactions, it's just hard to do better sometimes.
Yeah.
For some of these reactions. So what he does now is he gets for this value by solving all the algebra here, he gets the fixed value for the H2O. Just pull it back up. Website's a little. Right. So for now, he gets an enthalpy for H2O that just comes statistically from all those algebraic solutions, and you get an uncertainty for it as well, which is really nice. So these uncertainties are actually better than any of the ones you'll find on this. This is by far the most accurate value for this number in the world. So what I want to finally say is that every molecule in some sense gets assigned an enthalpy value. Every molecule has an enthalpy value. And that enthalpy value is unique to the molecule. And as you can tell, it's different. Right now we can specify differences between water and something else. Now we have differences of energies between the liquid and the gas for water. Now that's a really interesting point, right? Now let's think about that now. One thing that's really interesting here that we can notice is that the enthalpies for formation, what that is, I haven't mentioned that label yet, I should do that in class. What this means is they're very different between the gas and the liquid. All right, we were talking about condensation and evaporation when we discovered in CO2 that when we turned on our attractions and our size that we got condensation. And we noticed that when the system starts to condense, it's as if every molecule you put into that container condenses out because the pressure doesn't rise in. And as it condenses, the pressure stays flat as you feed more molecules in. Right, but then again, we thought that was, they probably thought that was a little strange. We would figure that we're feeding more gas in that the pressure would rise, but every molecule of gas we put in there was compensated by another molecule, or the molecule we put in, condensing out. And as that's happening, right, we're taking gaseous water and converting it into liquid. There's a massive heat difference that changes. So let's look at that a little more carefully. Right, so let me just redraw my little container. 15 minutes break. I'm going to cap this off now. I'm just going to cap it. We're going to make it constant volume at the moment. Cap flask. And we're going to make it an isothermal bath. And off the side of this, we're going to put a little inlet where gas flows into. And we have a pressure meter here. The barometer. I can measure the pressure. Right, so this is a slightly different measurement than we've done before. This is at constant volume. Right, we've capped the mass, we've capped it. It's also at constant temperature, but we can change the temperature if we want. Constant volume, dV is equal to 0. Right. So that's a little different than constant pressure, right? There is no exchange allowed. We're just feeding in, basically we have a pressurized vessel. Right? You can think of this like a pressure cooker. Right? A pressure cooker is a constant volume environment. No volume change. All you have is heat and pressure. Right? The term for this is called an isochoric process. I forget what core means exactly in Greek, but it means something to do with space or volume. Volume isochoric. Now, the unique thing about an isochoric process is because the volume cannot change, there is no work done in this system. Remember, work is PdV. dV is 0. So the net work in the system, net PV work, which is PdV, is 0 by definition. So what that means is that any change in heat, any change in energy, all du, so du is just equal to TdS. It's all heat. No work. Okay, so right, what am I going to observe now? Right, so now let's think about that a little bit. So now what I'm going to do is I'm going to, let's do it like this, right? I'm going to remove flask from bath. And I'm going to slowly start feeding in gas. Right, now I'm gonna empty it. I'm gonna empty flask initially. All right, so I'm gonna start feeding in gas, right? And so the gas is a appreciably low density that the entire system is gas. Right, so at low pressure, we have all gas. Right, and again, I have a barometer. And then because I don't have a bath anymore, I'm going to add a thermometer as well. Stick it out this side. Okay. And I'm going to continue feeding in gas until it begins to condense. Right, so I form some small amount of liquid at the bottom. And I have a little bit of gas. Oh, sorry, that's the wrong one. There's my thermometer. Kind of looks like the flask is smoking a joint, but I promise you it's just the one. Right, so the pressure has increased, but now we've started to condense the gas, right? What happens when that does it? Well, the pressure goes flat, right? Remember, right, as we feed in more gas, we get more liquid. We get 100% conversion liquid. Right, so eventually we have something that's mostly liquid with some gas molecules at some pressure. And we'll say this pressure, we'll set the pressure to be PCO2 at this pressure, and the pressure still reads PCO2. Right, so the pressure hasn't changed between the two steps, right? Because remember that all the gas we put in there condensed out. What do I read on the thermometer now? So before it condensed, right, we read the thermometer, and the thermometer reads 298.15 Kelvin. Right, we've got room temperature at this. Right, we're just reading in room temperature gas. And then what happens is that the liquid starts to condense, right? The gas starts to condense. Right, so here we just have at this point just CO2 gas. And during this process, we're taking CO2 gas as we feed it in and converting it into liquid in this process. So there's a new process occurring in our flask at not constant pressure, but constant volume. Right, as we increase the pressure, eventually we hit that critical amount that starts to condense. And then the pressure doesn't change, but the system continues to condense. So the system's not compressing, but there is some sort of there's some sort of chemical process, physical process occurring where it's converting gas to liquid. So it's doing something. It's just not it's not doing PV work. Right? And I want to know what the temperature is at the final point. I don't know exactly what the temperature may be, but I want to know if it's changed at all. Okay, well, let's look at that, right? We can use enthalpies to determine that, right? If this, right, so instead of here, we're just feeding in gas freely, that's no problem, we just compress it. But eventually we get to the point where it starts to condense, the condensation turns on. Right, and the heat change due to that event has to do with the enthalpies of gas versus liquid. So let's go look them up. So what we need to think about is the enthalpy of this change. What do we call the process of turning a gas into a liquid, besides condensation, does anyone know another term for it? We'll just call it condensation. I shouldn't be that fancy. Sometimes it's called fusion. Right? And that's going to be equal to the enthalpy of CO2 liquid minus the enthalpy of CO2 gas. Now let's go look these up really quickly on ATCT. Right. CO2 gas has a enthalpy. Yeah. So let's look up the liquid one first. It may not be here. Okay. Not all of them are available, so let's go look at on here. So it's hard to find the liquid value, but what I can do is find the value for this difference. And so this is whatever the liquid value is. And then minus 393.477 kilojoules per mole. That's the gas phase value I'm reading off from the right side of the screen. The enthalpy of formation of CO2. And I just read on here that the enthalpy of vaporization, which is the opposite of condensation, is 16.7. So this is equal to minus 16.7 kilojoules per mole. All right, so you can calculate, right? So that means that roughly the enthalpy of liquid is roughly 16 kilojoules per mole higher in energy than this, right? So we're losing energy. Right, so what this means is that the enthalpy is negative for this process. This is exothermic. Okay, so the CO2 releases heat when it goes from gas to liquid. All right, so what would you expect the temperature to do?
Go up,
Go
coming
up.
down.
Or go,
Well, wait,
that's an interesting question. Should it go up or go down?
down. It releases heat.
Releases heat.
Okay, so
So
down.
the temperature decreases. So what we should observe,
Delta T is negative.
yeah, that we should evaluate that delta T is less than 0. We should observe a decrease in the temperature because the system has released heat to the exterior, right? So the internal heat of the material that we're measuring inside of here has dropped by 17 kilojoules per mole, which is expressed as heat. That heat has been removed. So therefore, the temperature we measure on the inside has dropped. Right? What we would then feel, of course, is heat radiating off of the material, right? So that if we put this in a bath, right, the bath temperature would increase, but the internal temperature of the material would decrease instantaneously.
So this is why, like, when you have like a propane tank, well, like the little camping ones, right? It's all liquid propane in there,
Yeah.
but it's, I mean, I guess to be a liquid gas, it has to be super cold, right? I guess that's the
So that
secret.
also has to do with the pressure as well.
So it is
That is
related
that
to that.
too. So here's a good example. Right, so what this is saying is that the temperature of the materials decrease, but what you would feel on the outside, the bulb itself that would feel warm, because it's emitting heat. So think about the opposite of this, not condensation, but evaporation. You're hot, you sweat, and as you're hot, your sweat evaporates. What does your skin feel when it evaporates?
Wet.
Well, okay.
Oh, well,
okay.
sticky.
No, not okay. We're
Dry.
dealing with temperature, not feel. What cold, right? It cools. Right? Evaporation cools, right? And the reason why is in order to evaporate, you have to do the opposite of condensate, meaning that the liquid has to absorb energy from the outside to evaporate. Right? So it costs energy to evaporate. The energy gets pulled from your skin, right? The material in contact with the sweat, the energy gets sucked out of your skin, and so your skin's temperature decreases in order to facilitate the evaporation. This is the opposite. Here you would feel a warming sensation because the material itself is emitting energy. So here the bulb gets hot.
I was gonna say, I was thinking like maybe why you feel hotter in like a humid environment, but you'd be sweating there too.
Yeah, and that has to do more with
Not being able to sweat.
exactly. Yeah, the problem is it's hard to evaporate when the air is already saturated.
Yeah.
Because you can't add more water to it, because then it just condenses back out.
Yeah.
So the bulb gets hot, but the material gets colder, and vice versa for vaporization. Okay? So this is the thing, right? So this is why I don't have the slide anymore, but when we looked at this, well, maybe I'll just pull it up really quickly just to finish off, because we're just done in just a second. Let me just pull up one more slide. I just want to close this out, right? So phase transitions cause, or at least melting, vaporization, condensation, they cause a heat change in the material. It requires some amount of energy in and out to change the phase. And so we can kind of look at these compression curves again. Again, these are the curves that we see in our flask at constant volume. At high enough temperature, the liquid never condenses, right? It just compresses like a gas. But once we cool it down enough, at low pressure, this is low density out here, it compresses like a gas, and then you hit that critical condensation point where now the pressure is not increasing anymore. So what does that mean? Well, that means that when you're feeding in this initial gas right here, you're feeding in more gas and making it more dense. All of the energy, all of the heat energy that you're bringing in from those new molecules is being used to facilitate the phase transfer or the phase transition. So instead of using energy to do PV work, right? As I feed it in, you're feeding in more heat as you bring in more molecules. And that heat is being used in a gas for PV work, so the pressure increases. Right? The heat is all being used for expansion work in a gas. But in a mixture of liquid and gas, with just gas, you get compression. And then all of the heat that you would otherwise use for compression gets used for the phase transition. So the PV work never changes. You never get more heat into the PV work. You just get all of that energy is being used to condense out, or either it's being absorbed or emitted, whichever way you want to look at it. Right, so we don't see any pressure change because the sample is not using any of that new energy to actually expand and suppress. So here the energy stays constant, basically, while the energy is not constant, but the system is constantly phase transitioning and using all of the new available energy for that phase transition. And then suddenly you've converted all of it to liquid and it compresses again as a liquid. Of course, liquids compress very poorly, so this goes skyrocket. You compress the liquid. All right, so this is that enthalpy, right? The fact that this is flat means that the energy is being used for something else, which is the phase transition. And a great example of this, and we'll talk about it next class, is boiling water. You boil water at 212 Fahrenheit, but as it boils, the temperature never increases. The moment the water starts boiling at 100 Celsius, the temperature is 100 Celsius. You come back 10 minutes later, it's still 100 Celsius, even though you pump more energy into it. Right? You've got the stove on the whole time. That's because 100% of that heat energy is being used to facilitate the phase transition and not to heat the liquid. But basically, the temperature of the liquid never changes because any heat's going into it is caught, or the pressure, the heat of the temperature of the gas has not changed at all. Energy of the gas not changed at all because all that new energy that comes in is being used for the phase transition. It's the same idea with boiling. So we'll look at that more carefully next class. And then we'll look at a series of phase transitions that involve no heat change. It's one. Right. Have a good one, guys.
Oh, I'm using my late homework for the homework.
That's fine.
Okay.
It'll all just get tallied up at the end of the semester, so. Have you not turned it in yet?
No, but I will, no, I have like one part left to do.
Okay.